Okay, my name is Silas Eichsteller, and I'm going to talk about extracting data from graph images with AI. So I work as an engineer at a consulting firm called Computas in Oslo, Norway, and I grow my own cherry tomatoes. In my spare time, I like to watch some TV shows, and of course, one of my favorite snacks are indeed cherry tomatoes. So I take one out, I eat it, and sometimes I also do some statistics over it, like how fast I consume them. So we started off with like 21 cherry tomatoes, now we're down to 20, and then maybe I eat some more, now we're down to 12, and pretty soon there are none left. Another way to visualize this would be to plot it in a graph. So here in this example, we start off with 6 cherry tomatoes. At a timestamp, we eat one, then we eat another one, and then we eat maybe 2 at once, and so on and so forth, until we got 0 left. So every time we eat a cherry tomato, we can call this an event point. That's where the population of the cherry tomatoes get reduced. And we could also say, instead of saying we started off with 6 cherry tomatoes, we started off with 100% of cherry tomatoes, and we ended up with 0%. So this kind of graph is really common in the pharmaceutical sector, and it's called a Kaplan-Meier graph. And it's really characteristic about this like left to right stair shape. Of course, you can plot multiple tomato experiments in a single graph. So here are like a bunch of cherry tomatoes brands you can find in Norway. I don't think any of these are really grown in Norway, but these are a couple of experiments, and I plotted them all in a single graph. So unfortunately, I don't keep this paper I've written down all the data series around, but often I keep an image around. But if I now do another tomato experiment, if you will, and I want to plot it in the same image, this becomes kind of hard. So I kind of need to extract the original data back out again of that image. So I want to, there are different ways you can do this. We can, of course, try to do it manually, to like reverse engineer the event points and figure out the data series. But it would be cool to do it automatically. And if you want to do it automatically, we immediately see that there's a lot of challenges here. For instance, we have a lot of occlusions, which means that the plots themselves are overlapping each other. There's a lot of crowdings, which means that the plots are really close to each other, or there are other noisy elements in the graph image. And there's a lot of crossings. The plots cross each other all the time. So of course, we're going to use some sort of computer vision model for this. So there are different kinds of computer vision models out there that do different tasks. One task would be classification. It just says tomato and pear are in this image. Another type of model is that it does object detection. You can draw like a bounding box around the objects you detect. So tomato 1, tomato 2, pear 1. Or you could do semantic segmentation, which would be like classifying each individual pixel and say this pixel belongs to tomato, this pixel belongs to a pear. And then you have like the combination between object detection and semantic segmentation, which would be to say this particular pixel belongs to tomato instance 1, and this particular pixel belongs to tomato 2. And for this type of problem, we're going to use instance segmentation. More specifically, we're going to use a kind of specialized instance segmentation, which is called occlusion-aware instance segmentation. So if we look at this pear to the left, the model we're going to use needs to kind of know the shape of the pear behind the tomato too. So we kind of need to understand how it would look like. That would be occlusion-aware instance segmentation. So what we did some, or what I did some research on this to try to figure out different ways to extract plots out of images, and found some papers that did this, and also some open source data models I could use, or like machine learning models to do this. So the one we were using like at the beginning was just really specialized extracting and isolating plots in line images of line charts. So we used it, we scanned through the image, and it would isolate the individual plots in the image itself on their own map. If we zoom a little bit closer in, we can see that this is how a detection map would look like, or more specifically, it would be a binary map, which means it's like black and white pixels. White pixels means it's a detection. Black pixel means it's not a detection. And of course, it would be a pixel level. So if we brighten things up, we look a little bit closer at the pixels. This is how we would want it to look like. Unfortunately, this is how it looks like. It's a little bit more messy and a little bit more noisy if we zoom really close on a pixel level. So we need to clear things up. We can use some classic computer vision methods for this, something called morphological operations, among others, something called skeletonization, which would reduce the width of the lines to a single pixel. Then we can do some groupings. We first find all the horizontal groups potential horizontal groups in this particular line. Then we do some voting and some other ways to try to reduce the grouping to really figure out which are the horizontal groups. And also, if groups are really close to each other, we also need to do some rule of thumb logic on that one. Then we do the same on the vertical groups. So we group them together and use, among others, the fact that we know it's like a stairway shape to reduce them to the actually groups that are the ones we can continue using. So if you now blend in both of these horizontal and vertical groups and extend those groups, where they intersect, that's our event points. Except it's just the event points on a pixel level. It's not the event points in the context of the graph itself. So what we're going to do now is going to try to use an LLM to help us out a little bit. So we have a wish list. We want to get the X and Y axis units. We want to also get the legends, maybe. And we're going to send this image alongside with our wish list over to an LLM. Originally, we were thinking like, oh, could we not just use the LLM or a multimodal LLM to just do this entire task for us? Like, why would we, could it just extract the data series? And did a lot of experiments with it. Unfortunately, LLMs are not there yet. And there was a lot of hallucination and inconsistencies with this. But what they are really good at is extracting metadata information. So they can extract like XY units and also like the legends used and stuff like that. So it returns some sort of JSON, which we can use to then take the X and Y values we figured out earlier on the pixel level to map over to the actual X and Y values in context of the graph itself. And this can, of course, be done for all the plots in a graph. So where is this used? I teased it a little bit before. It's used in the field of medicine, mostly. So, and we built like a similar system like that for a customer of ours in the field of medicine. So there's a lot of papers out there, and some of them have Kaplan-Meier graphs, but they don't release the underlying data for creating those Kaplan-Meier graphs. So if we want to compare different papers with each other, or you want to do some other statistics on these graphs, you would need to manually try to extract the data back out again. So this system, what we built, was helping to extract this automatically. There's a bunch of papers out there. It doesn't need to be in the field of medicine even. It could be about the aerodynamics of cows, or it could be about the survivability of Harry Potter characters. With a lot of papers, there comes a lot of different Kaplan-Meier graphs. You can see there's a big variety in here. There's some of them that have like dotted lines, different background colors, crazy shapes, much noisy data points. Some of them are really pixelated even, and that is a problem, at least for this model we originally were downloading just and using to extract and isolate the individual plots. So what we did now was fine-tune this model. So it's really easy for us to generate Kaplan-Meier graphs. It's not that hard. It's really hard to extract the data back out again, but it's easy to generate. So we could just generate thousands and thousands of Kaplan-Meier graphs and do like a lot of variations to them, do a lot of data augmentation. And alongside, we also generated the corresponding binary maps for isolating each of these plots. And by doing this, we fine-tuned the model to basically be more consistent. So we can see here like an example of a before and after. We can see that it became much more continuous. It understands the structure of the line. It's not perfect, but we can still use like the classical machine learning approaches to clean things up afterwards. And we really did see that it managed to cut through the occlusions and the noise in the data. It could understand the crowdings, and it also understood the crossings, when the lines were crossing each other all the time. So this is how we use deep learning vision transformers, which we fine-tuned in combination with classical computer vision to clean things up and also extracting the event points as a pixel value, and LLMs for getting metadata information to map it to the actually value in context of the graph itself to, yes, extract the data points out of images of, in this particular example, Kaplan-Meier graphs. Thank you very much. Well, if there's any questions, you could ask, of course. I guess we got some time left.